Okay, I'm going to start with Chapter 4, Part 2, and we're going to look at forces. And basic definition is influence that causes a body to deform or accelerate. Okay, um, so when we look at forces, initially we're going to think about them in terms of equilibrium. Okay, and for it to be an equilibrium, that actually is classified underneath engineering statics, which is one of the courses you'll take as part of the engineering curriculum. And the idea is that if you took all the forces and all the directions of those forces, when we're talking about static equilibrium, if you took all the forces and all the directions of those forces and summed them all together, you basically have a body or a physical object that is not in motion. Okay. Now, you could also have an equilibrium condition where a body is in motion, and we classify that typically as dynamic equilibrium. And this one is the case where you have something moving, but it's not accelerating, so it's not changing in terms of its the velocity isn't changing essentially. It could be a car driving down the street at a constant speed and constant direction, and it's at a constant elevation. And what you wouldn't what you would realize is if you looked at the analysis, you'd find that the forces that are acting on it, you'd have like a force of friction and a force of air resistance pushing back toward the car, and then you'd have the engine propelling the car forward, and those forces would cancel each other out. Essentially, the friction and air resistance going toward the car, and in the direction opposite the motion of the car, and the engine trying to propel it in the other direction. And then vertically, what you'll have is the weight of the car, and there will be an equal opposite force pushing back up from the ground, the normal force. And if you took all those and summed them all together, they come out to be zero. Of course, you have to include the directions as part of that. All right. Now, when you get an imbalance in those forces, what you get is acceleration. Right. And that actually is covered in engineering dynamics. Okay. All right. So let's continue on. Okay, so there's certain types of forces, or here's some common ones. What we're going to be looking at: contact forces, so two things connect, pushing against each other. Gravitational force, or weight, typically directed down toward the center of the Earth. Cable force, we'll look at. Cable force is acting along some axis of the cable, so it's like in the same direction as the cable. And that's under tension. Then we have pressure force, and this is when you have a force that's acting normal to the surface. So you take an object and you put it down, below the surface at some depth, and you'll have pressure acting on it. The further you go down in that, if it's in water, let's say, further you go down, the pressure increases. Okay, and the idea is that it's typically, what is it defined? It's defined as a force per some area, cross-sectional area, or some area normal to the surface. Then you have another one, fluid dynamic force. Okay, so you have some force when, this is like the force when a fluid goes around a body or through a pipe. And an example of that would be like the force of lift for a wing for an aircraft, because as the velocity of the fluid, in this case would be air, travels faster over the top of the wing and it's curved, it causes a reduction in pressure on top of the wing as opposed to what's underneath, so that causes lift, or one of the ways to get lift anyways. Okay, so this is just a definition of some of the common forces. All right, so what we have to realize, and this is the same idea we had previously with vectors, right? So really would have some magnitude, a direction, and sense. And sense is just really the sign, is it positive or is it negative? Okay. Sometimes you won't see this being defined. They'll just have a magnitude and direction by themselves. They won't bother with this is also as part of the direction. So how it's defined, you might see just magnitude and direction as opposed to magnitude, direction, and sense. When we have more than one force acting on a body, we call that a force system. Okay. Stress. Okay. Stress is, and I'll take a look at an example to show you these, actually both with stress and with when you're have a force problem. A force problem in equilibrium is what we're going to be looking at first. Okay, so stress is when you actually applying like some force to an object. Okay, and what happens is when you apply a force to an object, you get some deformation of that object. Okay, depending upon what it is. If it's a marshmallow, of course, you apply some force and it deforms quite a lot. If it's a steel, steel support or an I-beam, you apply some force to it and it doesn't deform much, but it does deform. Okay, so that's one of the things we'll have to think about. So depending upon what the material is, for the same amount of stress, you would get different deformation, right? And the deformation is called strain. All right. So we have, there's basically two types of stress. There's normal stress. Normal stress is like acting perpendicular to the plane of the axis of the body, let's say. So you have let's say you have a column, cylindrical column, and you're pressing down on the top of that column. That would be considered like normal stress. You could think about it as in terms of like a support for a bridge or building, let's say. Okay. And the other one is shear stress. This one is like, stress parallel, tangential to the face. So this is like, two surfaces, two parts of the surface where, you have a force that's actually in the same direction of the face of the material. Okay. So it'd be like a force on the side, let's say, of your column. Okay. But we're not going to cover that here. All right. So here's our normal stress. And we have two different types. We have either, tensile or compressive, right? So it's like pushing in, both things pushing in, putting this column under compression, let's say, or this cylinder under compression, or rod. And in this case is like they're trying to pull it apart, okay? So that tensile is when the forces are acting outward, trying to stretch it, and compressive is when it's trying to squeeze it together, essentially. Strain. Okay, so this is the deformation caused by that stress. So it could be you apply some force on this rod here, or apply it on here. What happens? The length changes. In this case, it shrinks a little bit, and this one it stretches a little bit. And how much does it stretch? It's going to be dependent upon cross-sectional area and what this material is and how much force you apply, essentially. Okay. So two types of strain, same idea. In this case, we're not going to look at the shear strain. We're only going to look at normal strain. So like I said, how much does it deform divided by the original length, okay? So it's like a ratio, right? Okay, now we can look at a stress and strain diagram. And we have, basically like we can think about the different points on here and the different regions. If we have a real basic plot or diagram, it actually is, real materials. A little more involved in this, but it gives us kind of the idea here. What happens here is that here's stress, so you add some force for some cross-sectional area on let's say, a column. And strain is how much does it deform. So you increase, this is basically force per however big it is, because I said like whatever this is a cross-sectional area of a specific object that we're looking at. And what happens is you add more and more force, it deforms in a so-called linear fashion. So, you double the force, essentially you get double the deformation, or, double the size of how much it increased in length or decreased in length. So that keeps going as you add more and more force. And then you get to this so-called elastic point where you're at the limit or elastic limit. And at this point, if you apply any more force above this, what happens is it starts to deform, okay? And the deformation is different than what it is here, because in the elastic region, if you remove the force, it'll actually go back all the way down to here. It'll retain its shape. What happens here is that now you've actually stretched the material too far where it won't retain its shape when you remove the force, okay? That's considered to be the plastic region. If you keep applying more and more force from that, you get to the ultimate stress point, and then it just kind of goes right along, and then it fails, okay? And this is just showing, the reason this is because at this point it starts to stretch out. So it actually, it removes the stress a bit because it's stretching out, but then you get to a point where it has a complete failure here. Okay, so it just sort of, here is kind of like the limit of what you can do. You can actually operate it before it breaks apart, right? Now we can look at this in a little more detail. Here's another graph, okay? And in this one, we have like this intermediate region in here, which is between the elastic limit and the yield point. In design, generally you want to be down in here somewhere around here, so you don't even get close to that elastic limit. Although in this case, it won't fail, right? Between here, it's not going to fail, but it will deform, right? It deform in a sort of a linear fashion, somewhat linear fashion. And then at this point, the yield point, it's about it. That's about it. And there's really not much of a difference between the ultimate strength and the yield point here. It's slightly higher, okay? And then you get into the last region where it just breaks apart, okay? So if we look at those a little bit more, we have the elastic region, right? The plastic region where it's permanently deformed. And then the rupture range where you're up in that area where a rupture region where you have a fracture and that's essentially it. It just fails, breaks apart. Right. And the points are, we have the elastic limit, and we have the yield point, the ultimate stress point, which I talked about. And then this region between the elastic limit is the non-proportional elastic region. Okay, so you start to get, it starts to deform, but it does it in a so-called non-proportional fashion, but it does return back to its shape, okay? And the next one is, we'll talk about design stress and just some terminology used. The maximum stress for it is called the allowable stress, okay? And typically, this is going to be your limit, right? Your elastic limit. So your design needs to be defined in elastic region, realistically, okay? And you're actually kind of low in the elastic region, depending upon, if weight, you have different concerns. You have to be, if your weight is a concern or not. Maybe it's a big concern, or maybe it's not a big concern. So depending upon that tells you kind of where you're going to be in elastic region. Of course, there's other trade-offs associated with weight. Like if you build it too big, then of course the structure itself could have a lot of weight, which is a problem, and cost associated with it. Okay. So how do we determine the design stress? All right, was one of the questions when we're going to be looking at the problems. All right. And that will be one of the things we'll go to solve. But for now, I'll just go through it in general. All right. Now, when we are designing a system, we have design uncertainties associated with it, right? So it's like, well, I'm going to design a system. I'm going to have a certain expectation of how much force is going to be on an individual cable or column or rod. And those are considered to be like my loadings, okay? But, you may not have anticipated everything, right? So if you're designing a bridge, and you think, 100 cars going across it at one time might be the most you ever have. Then it's like, well, maybe you didn't. Maybe someday they have military parade in their tanks or something going across, or heavy tanker trucks. Okay, so make sure you have these things, uncertainties. How accurately did you really represent that sort of peak load? Okay. So the other thing is failure mode. You might not have anticipated every way this thing can fail, right? Your system could fail, and usually, well, in general, you can think about it's only as strong as the weakest point. Okay. So in terms of forces, like did you anticipate all the different forces that are acting? Did you figure with, let's say, wind, earthquakes, and the other properties? Okay. Physical properties suffer with different variations, right? So you might have a standard that you had designed, you have a certain expectation that a certain material can handle certain forces or certain characteristics of certain materials. What if they're out of spec a little bit? Okay. Deterioration, all right. So it could be, after rain and wind and everything, it starts to break down the material that you use. So as a after some period of time, it's actually getting weaker, all right? So the characteristics of, the stress strain diagram actually changes somewhat due to deterioration in the real system that you're doing, analyzing. And then the analysis. You're making some analysis, you're making assumptions typically, and the results are approximations. And you could make some errors associated with your in your calculations when you're doing an analysis, right? So these are design uncertainties. So that's why we have this other thing, and it's called factor of safety, okay? So what this really means is essentially you're building in some factor of safety. So let's say that the real point at where it fails, at least from the theory, could be here. And then what you do is you make this one a lot smaller. So you might say it times 2. So you might say, oh, I know it fails at 100 newtons per square inch, and that's what I have for failure for that particular column. But then I say, well, I shouldn't, to make sure, because of all those design uncertainties, I make the allowable, instead of 100, I'll make this 50. And now I'll have a factor of safety of 2. Okay? So you want to make sure that when you design it, that it meets the allowable, right? So it doesn't go above the allowable because of those uncertainties. Okay. And a couple of things is that, high risk structures, you might set the factor of safety equal to 3. So you might make this 100 and make this 33, let's say. And if it's something, maybe it's you're designing something that you really have to worry about weight, then you might make a factor of safety close to 1. Could be maybe in a spacecraft, let's say a rocket, something like that. Okay. So this is one of the things we do, and as the analysis, we do our stress and strain analysis. But when we do that, one of the things we want to say, well, here's my analysis. Will this system fail? Will this column hold the weight, or the system fail under certain conditions or not, right? And it might be certain forces. The forces that are acting to pull the cable apart, and that maybe like I said, maybe this is 100 newtons per inch squared, that it could before it fails. But then you say, well, I'm really going to make sure I design it so that it's below 50 newtons, and that would be a factor of safety of 2. Okay, so that's one of the things we need to do. So we work this factor of safety in there to make sure that in a real system that we've addressed these design uncertainties. Okay, and that's pretty much it. I'll take a look at some examples to show you actually going through these things, doing the analysis. There's one example in text I'll take a look at that's very good. It has the different parts of it. So here, if we're doing vector unknowns, we use law of cause and parallel. So we could use a parallelogram law to solve these for vector unknowns, but for vector unknowns or unknown vectors. Let's see. So we usually don't use that. Usually we use component method. All right. Also, vectors are very useful representing forces. We see that. Stress is a force per unit area. Strain is a measure of how much it deforms when you apply that force, that normal force. And factor of safety is measure of overdesign. All right. So that's pretty much it for this chapter.